covariance and the variance of sums. Let's state a very basic theorem. So first let me write the title of the section. Covariance and the variance of sums. Okay. So we have this theorem that says the following, and it's a very good test problem. If x and y are independent, then for any function h and g, for any functions are g and h, the expected value of e of g times h, e of g times h, is just the product of the expected values. It's e of g of x times e of h of x. Now, to prove this, it's going to be in two cases. The continuous case I'll do first. Okay, so suppose that x and y are jointly continuous, with the joint density being, naturally enough, f of xy. Okay, so we have the following. E of g of x times h of x, this is nothing more, excuse me, here, this is the big typo that I have. It's h of y, because we have two random variables, x and y. Sorry about that. E, the expected value of g of x times h of y, well, this is nothing more than a double integral from negative infinity to infinity on both limits of whatever in here, g of x times h of y, times the density, the joint density f of xy, times dx dy. Okay, but let me just show where it says this. X and y are independent, so then this function is nothing more than f of x times f of y. So let me go to the top, please. Okay. So like I said, this is nothing more than f of x times g of y. And using that fact, we can now say the following. This integral from negative infinity to infinity, negative infinity to infinity, of g of x times h of y, and fx of x times fy of y dx dy. Now, what I just underlined is only a function of x, and what I'm underlining now is just a function of y. I can separate it. Integral from negative infinity to infinity. Remember, this integral goes with the dy. So I can put the fy of y times h of y dy times the integral of g of x times fx of x dx. I can put this in front of that inner integral sign. And then, since what's left over, namely this, including dy, namely this, since this part has no y's in it, I can even bring the y in front. And that is what I did. Okay, and here's where this theorem comes together. That's nothing more than e of hy times this integral is nothing more than, let me write big brackets, that second integral is nothing more than the expected value of g of x. And there it is. There it is. 100% definitions. Okay, now we do the same thing, but we do a continuous case. There's no doubt that this would definitely be a candidate for a test problem. Prove the following. For the continuous case, so proof continuous case, suppose x and y are independent, discrete, random variables with probability mass function p of xy. Okay? So what is the expected value of g of x times h of y? Well, it's just here. Integral becomes summation. It's the double summation over x and y of g of this, g of x, or h of y, times the probability mass function, p of xy. So this is the summation over x times the summation over y of g of x, h of y, times this. But since x and y are independent, it's just p of x times p of y. Okay, now, like before, I can bring this in front of the first summation, because first summation only has to do with y's. G of x is a constant. So is this. I mean, if you have the summation as x goes from 1 to 7, and you have 3x squared, this has nothing to do with x's. You can bring it in front. You can just add up the x squares, and whatever that sum turns out to be, multiply it by 3. And of course, x goes from 1 to 7. X still goes from 1 to 7. In the first case, you'll get 3 times 1 squared plus 3 times 2 squared plus 3 times 3 squared, all the way up to 3 times 7 squared. But each one of these terms have a 3 in it. So you can factor out the 3. So you get 3 times the quantity 1 squared plus 2 squared up to 7 squared. But this is this here. You can factor out the constant. And that's just what I'm about to do after I clean up this stuff. So this is equal to the summation over x of g of x times px of x times the summation over y of h of y times py of y. And this first summation is e of x, e of g of x times the second summation, which is e of h of x. And there it is. We did prove it. And all I did was just use the definition of our expected values. E of anything is, discrete case, is the summation of the anything times the probability function. Integral, e of anything is the integral of anything times the PDF dx. In double variables, it's a double integral. Okay. Let us define the covariance. The covariance of x and y is denoted COV, covariance of x and y. And by definition, it's an expected value. It's an expected value. It's the expected value of x minus the expected value of x times y minus the expected value of y. Okay. Wonderful. But that's the definition. 3 lines means definition. This has no meaning until we say, oh, we're defining this to be this mess. The right side has meaning. Now, let us get a different definition of the right-hand side. First, let's work on what's in the brackets. Let's distribute. X times y minus x times b of y. So those should be those closed type brackets, minus y times v of x, minus or plus e of x times v of y. Now, need to remember a couple of things. The expected value of a constant times x is just the constant times the expected value of x. And the expected value of just the constant is the constant. If the random variable x is always 9, 9, 9, 9, 9, what would you expect the expected value to be? Answer is 9. If you multiply the expected value, if you multiplied each and every value of x by k, it's not reasonable to think that the expected value of x would be multiplied by k. Okay. All right, now when you take the expected value of x or y, you get a constant. Get an exact value. So first, we take the expected value of xy minus the expected value of this. But e of y is a constant, so it comes out in front. Let's do that maybe in 2 steps. It's one of the theorems I just wrote in the bottom and erased. You have the expected value of x times a constant. E of y is a constant. It's going to come in front. So you're going to have e of xy minus e of y times e of x, because you get e of x, minus e of this stuff, e of y times e of x. But the e of x comes in front because it's the constant times e of y, plus e of this product. That product is a constant. E of x is a constant, e of y is a constant. You multiply them, you get a constant. And when you take e of a constant, you just get the constant, e of x, e of y. Okay. If you take away e of x times e of y, and then you add it back, it's 0. So all that survives is this. You get e of xy minus, I'll just commute that product. Instead of e of y times e of x, I'll say e of x times e of y. So this is another way of calculating the covariance of x and y. And anytime you forget it, all you do is distribute this product. Just distribute the product from the definition. So those are two ways of expressing or calculating the covariance of x and y. Those are two ways to calculate the covariance of x and y. Unless you have to prove it on an exam, you can basically take it as two different definitions. Okay, so now, what if x and y are independent? Well, we just said that the covariance of x and y is e of xy minus e of x times e of y. But that's going to be 0. Because since x and y are independent, I can take the expected values. The e of a product of independent random variables is just the product of e of the random variables. E of x times e of y. I have e of x times e of y, but look, that's exactly what I happen to be taking away. And even if I don't know what e of x times e of y is, I know one thing. If I take it away, I don't have to know what it is. The difference is 0. I don't have to know what e of x times e of y is. Okay. So, if x and y are independent, then the covariance of x and y is 0. But is it true the other way? If the covariance of x and y is 0, then are x and y independent? And the standard way of doing this, you want to define y or x to be very, very simple. Define x such that p of x equaling 0 is equal to p of x being a negative 1, or p of x equaling positive 1. Let these all three be equal, and they equal the number 1/3. So that's what's going on with x. The probability that x equals 0 is the same as the probability that x equals 1. The same. And what is that common value that they all three equal? 1 divided by 3. I used less space than I anticipated. So that's x. Well, how are we going to define y? And that's kind of simple. We're going to let y equal, well, let me say this. We're going to let y equal 1 if x is 0. And we're going to let it equal 0 otherwise. That is, if x is not 0. Okay. So now, think about what x and y are always going to be. Well, actually, let us calculate E of X. Well, I know it's a sum, and it's over all x's times the probabilities. X can be 0 times its probability. 0 times the third. Plus, x can be -1 times the probability that is -1, a third. X can be 1 times its probability. If you do the math correctly, you'll see this is 0. You'll see that this is 0. Okay. Now, on the top right, I'm going to figure out the covariance of x and y. By one definition, it's E of x times y minus E of x times E of y. Okay. Now, what is x times y? Well, if x is 0, no matter what y is, whether y can only be 0 or 1, but no matter what x is, if x is 0, no matter what y is, when you multiply x by y, you get 0. Okay. What if x is not 0? Well, if x is not 0, then y is 0. One of these two will be 0. If x is 0, well then x is 0. So x times y is 0. If x is not 0, well then y equals 0. One of them will always be 0. Okay, so we have 0, x times y will be 0 minus E of x times E of y. But E of x, we just calculated. It's 0 times E of y. And E of 0, E of a constant is just the constant, which is 0 in this case. So this is 0, and this product is 0, because 0 times E of y is 0. 0 minus 0 is 0. And x and y are not independent. So the answer to this question down here is no. The covariance can be 0, even though x and y are not independent. They are not independent. Okay, knowing one will not affect the other. Let's go over some basic properties of covariances, of the covariance. Very basic properties. The covariance of xy is the same as the covariance of yx. Okay. The covariance of xy is the covariance of yx. You can switch what you're taking the covariance of. And what information, if anything, so how do we prove this? Or why is that true? Well, proof. The covariance of x and y is E of xy minus E of x times E of y. And x times y is the same as y times x, and this times that is the same as that times this. But this last line, this line right here, that's just not the cosine, but rather that's just the covariance of y and x. the covariance of Yx. So yes, that is true. Now, what about the covariance of XX? What is that going to be something special? Well, how you handle these things is you just get your hands dirty. You apply the definition. Well, it's E of this times that. It's E of X times X minus it's E of the first times E of the second, which is also X. So, you have E of X times X, or X squared, minus this E of X is being multiplied by itself twice, so you get E of X squared. And then you say, oh, look at that. That's just the variance of X. This happens to be the definition or a theorem that equates to the variance of X. You take the definition of variance of X, you can conclude that it also equals E of X squared minus E of X all squared. You multiply something in there by a constant. How would you show that the covariance of AXY is the same as the covariance of XAY, which is A times the covariance of XY? I'm going to show that this equals the last. First, I'm going to show that. Okay. So, what is the covariance of AXY? Well, by definition, it's the expected value of, I call this the first and that the second. The first and second are separated by a comma. Their expected value of the first times the second. Minus the expected value of the first times the expected value of the second. Now, what's in here is just A times XY. Told you, if you have E of a constant times a random variable, this is just A times the expected value of the random variable. X times Y is a random variable. The A comes in front of their expected value sign. The A comes in front of the expected value sign times E of Y. Okay, between this term and this term, they both have an A in common. So I factor it out. Get E of XY minus E of X times E of Y. Now, what's in those big brackets with the A in front? What's in those big brackets, by definition, is not the cosine, sorry. But what's inside those big brackets is the covariance of X and Y. That is, yes, the A can factor out in front. Okay, so now that we proved that one, there's no need to prove it to prove it again. I'm going to use this fact to prove that middle term in the top line, the covariance of X times AY. Well, the covariance of X comma AY. Let me change this marker, please. Well, we have our theorem. We've already proved that it was the very first theorem. We can interchange those two. This is the covariance of AY comma X. And we just proved that when you have a constant in front of the first one, you can factor it out. We just proved that. So we have A times the covariance of YX. there's my A, but the first theorem says that the covariance of yx is the same as the covariance of xy. That is, we now just proved that this is equal to that. That is, whether the constant is being multiplied by the first random variable or the constant is multiplied by the second random variable, the constant does come in front. The constant does come in front. The next one is this fact. I have to decide if I want to prove it or not. But it's important enough to at least to state it. We at least have to state this theorem. That the covariance of the summation of a lot of random variables, comma, the summation of a lot of random variables. Say I goes from 1 to n, and j goes from 1 to m. In other words, what is the covariance of x1 plus x2 plus x3, comma, y1 plus y2? What is that equal to? And basically, it's the covariance of xi, yj, xi, comma, yj, but we sum over I and j. J goes from 1 to m, I goes from 1 to n. In other words, we take the covariances of every combination. That is, we'll take the covariance of x1, y1, plus the covariance of x1, y2, plus the covariance of x2, y1, plus the covariance of x2, y2, plus the covariance of x3, y1, plus the covariance of x3, y2. You take the covariance of any combination of something in the first one with something in the second. Something from the first, something from the second. And you add them all up. You add them all up. That's what that one is saying. Okay. Let's try some other things. So, for example, if you came to know that the covariance of x and y is 11, what would the covariance of 3x comma y be? And, v. It would be 3 times 11. Okay, if you were told that e of xy is 4, and e of x is 2, and e of y is 5, what is the covariance of 5x comma y? Well, we know it's 5 times the covariance of xy, and the covariance of xy is e of that product of those two minus e of these things separately, e of x times e of y. Well, e of xy, we were given that to be 4 minus e of x times e of y, let's just say 40. Say e of xy is 40. Minus 2 times 5, which is 10. Minus 10. So you get 5 times 30. That's the covariance of x and y. So the final answer will just be 5 times that. It's important that you be able to work out these numerical examples. But it's just write down the formula and plug in the pieces they gave you. Okay. So how about we have the following. Let x1, x2, all the way up to xn be independent and identically distributed. Identically distributed. That is, they have the same probability density function. Well, identically distributed random variables. And you further are given that they have their expected value of mu, and the variance is sigma squared. Okay. So how about we let the average, we let x bar, well, this is going to be the sum of the x sub i's over n as I goes from 1 to n. You add up all the xi's and you divide by it. This is the sample mean. Okay. Now, we'll make a definition. We're going to define xi minus x bar I, or I can be 1 or 2 up to n, as deviance. Actually. Deviations, like standard deviations. Okay, we're going to define them to be the deviations. So x1 minus x1 bar is one deviation. x2 minus x2 bar is another deviation, all the way up to xn minus x sub n bar. That's it, the last deviation. So now, we'll define s squared to be, just like always, it's going to be the summation as I goes from 1 to n. It's going to be the deviance squared divided by n minus 1. And this is a random variable. And it's called their sample variance. So there are a few definitions here. I defined x sub bar. I defined something called deviations, and I defined their sample variance. Okay. So now, what if we wanted to find the variance of x bar? What if we wanted to find the variance of x bar? We want to find the variance of x bar. How much is the variance of x bar? Well, the first thing I want to point out is, if you have the variance of a times x, this is a squared times the variance of x. Okay? Okay. Now, remember that I defined x bar as the summation of x. I defined it as the summation of x sub I over n, as I goes from 1 to n, which, by the way, is the summation of 1 over n times xi, as I goes from 1 to n. The 1 over n in front doesn't have any i's in it, so this is 1 over n times the summation of x sub I. Okay, so what we want is the variance of x bar. But x bar is this. It's 1 over n times x, the random variables, the sum of the random variables x sub I. That is, it's what's inside here is 1 over n times x1 plus x2 plus x3 all the way up to x sub n. This is a random variable. The constant 1 over n comes out in front, but it gets squared. It's 1 over n, the variance of the summation of xi, as I goes from 1 to n. Okay. Let me get rid of this as well. Now, since we were told that these are independent, this is 1 over n squared, and I can bring the variance inside. The variance of x sub I, as I goes from 1 to n. This is 1 over n squared, and the sum of the variance of the x sub i's that was given to be okay. Each variance we were told was sigma. We were told at the very beginning, I erased it, it said that let xi through xn be independent and identically distributed random variables having expected values mu and variance sigma squared. Each one of these is sigma squared. That is, it's 1 over n squared times the summation as I goes from 1 to n, but this is always sigma squared. And when I is 1, sigma squared, plus I is 2, sigma squared, plus I is 3, sigma squared. We are adding this up n times, so we get n times sigma squared. This summation is n times sigma squared. And one of the n's in the top kills off one n in the bottom. You have 1 times sigma squared divided by n. Actually, it's not delta, but this symbol. Okay, so that is the variance of x bar. That is the variance of x bar. So, somebody tells you that x1 through x2 through xn are independent and identically distributed random variables was the expected value mu, and the standard deviation, the variance is sigma squared. Well, they tell you the expected value is 4, and sigma squared is 2, and they ask, what's the variance of the sum? What's the variance of x bar? Well, it's sigma squared over n. And I guess I should tell you n is 15. So you just say, oh, this is simple. The variance is 2 over 15. Okay, it's just plug in the values. Just plug in the values. Okay, let's erase this and try something else. So, this is the classic hat problem again. You have n men, capital N, m men leave their hats on a table. And then n, capital N men leave their hats on a table. And then they're going to randomly pick a hat from the table. Now, if we define x to equal the number of people who randomly choose their own hat. Okay? They're each going to randomly, each of these n people are going to go to this table and randomly pick a hat. I'll assume all the hats are similar in shape. You know, somebody had a really, really big one, you know, that kind of messes things up. You probably have a better chance of picking the big one. Okay, so we want to find the variance of x. Find the var of x. Well, here's the solution. X is equal to x1 plus x2, etc., up to xn, where xi is either 1 or 0. Either the first person gets their hat, so one person got their hat, one more person got the hat, or nobody gets the hat. It's going to be 1 if the ith person, so I call the subscript I, the ith person chooses their own hat. And it's going to be 0 if they don't choose their own hat. That is otherwise. So either x1 is 1 or 0. Either that's going to be a 1 or a 0. And when you add up all the 1s and the 0s, you will find out how many people got their own hat. Oh, that's x. That's how we defined x. Okay, now, not going to prove a lot in this videos lately, but we know the fact that the variance of x is the summation, is the summation, let me say it differently, is the summation of the variance of xi. Now I can motivate that I goes from 1 to capital N. I guess that should be capital N. That should be capital N. Plus 2 times the summation over I is less than j of the covariance, there I go again, the covariance of xi yj. So we have the formula in the very, very last line that we want to use. So we're going to have to know, for example, what is the variance of xi? Now, the variance of x sub I, well, by definition, it's e of xi squared minus e of xi, the whole thing squared. But now, xi is either 0 or it's 1. 0 squared is still 0, and 1 squared is still 1. That is, xi squared is the same as xi, x sub I. So it's e of xi minus e of xi quantity squared. Now, what is the probability, what's the expected value of the I of e of xi? What is the expected value? Well, each person has the same chance of getting their hat, 1 over n. So e of 1 over n is just going to be 1 over n. Over here, again you have 1 over n, but this time we square it. We have 1 over n squared. Multiplying the top and the bottom by n, our common denominator is n squared. We have 1 times n, or n, take away 1. That's the variance of x sub I. That's the variance of x sub I. Okay. So now, what we need to calculate is the covariance of xi yj. So let's do that down here. What is the covariance of xi yj? Well, by definition, it's e of xi yj it's the expected value of ei xi yj minus e of xi times the expected value of y sub j. Okay. So now, when is xi yj not equal to 0? When is this not equal to 0? Remember, xi is either 0 or 1, and yj is either 0 or 1. Well, only when the ith person picks their own hat will xi be 1. Only when the j person picks their own hat will yj be 1. You're going to get 1 only if the ith person picks their own hat and the jth person picks their own hat. So, what is e of xi yj? It's going to be, like always, the summation of x times p. It's going to be the probability that x is 1 and y is 1. Well, let's write this as a conditional probability. This is the probability that say, well, something's a little bit wrong. X sub I is 1 and Y sub j is 1. This is a probability that Yj is I, given that X sub I is 1, Y sub I equals 1, given that X sub I equals 1, times the probability that Xi equals 1. And unfortunately, I need to erase this bottom. Okay. Now, given that the ith person picked their own hat, because Xi is 1. Given that the ith person did pick their own hat, what's the probability that the jth person picked their hats? Well, we know their ith person picks their hat. So there is now just n minus 1 hats left, and only one of them can go to person j. The probability that the jth person picks their own hat, given that there's really just n minus 1 hats there, is 1 over n minus 1, times the probability that the ith person picks their own hat. Well, there's n hats, and it's 1 over n. That's E of xi ji, yj. That's this. This is 1 over n minus 1 times 1 over n. Okay. So let me erase this. Problem's a little bit longer than I really expected, but it's worth doing. Okay. So what is the covariance of x sub I, y sub j? The reason we did what we just did in the bottom is because, by definition, this is E of xi, yj minus, well, that is, we needed this. Well, we just found it. We just found E of xi, yj minus E of xi times E of yj. The first one is this, 1 over n minus 1 times 1 over n, minus, and the second one is 1 over n squared. This is 1 over n times another 1 over n. It's 1 over n squared. And if we got a common denominator for this, that would be, if you work it out, this would just be 1 over n squared times n minus 1. Yeah. Okay. So now, we know that the variance of x is equal to that formula on the very bottom that I erased. The variance of x is the summation of the variance of xi, as I goes from 1 to n, plus 2 times the double summation of the covariance of xi, yj. Okay. Let me erase some more. Hopefully you took good notes on what some of these quantities equaled. So when I write them down now, you say, yeah, we already calculated them. Now, the variance of our x sub I actually wrote this one down. The variance of x sub I is n minus 1 over n squared. That is, it's a constant. And when we add up that constant 1 through n times, it gets multiplied by n. So that part is n minus 1 over n. Plus, now, the covariance, this is in front of us. It's 1 over n squared n times n minus 1, and there's a 2 in the front. But what about this double summation, where i's are less than j's? What is that going to equal to? Well, from the n, we want to choose 2. We want to choose 2. 1 for I and 1 for j. And this piece here, well, it's going to be n factorial on the top, and on the bottom you'll have 2 factorial, which is a 2, which will cancel out with that one, and then you get n minus 2 times this mess. Okay. And believe it or not, something's wrong. N minus 2 is factorial. If you work this out, I'll do a little bit. N minus 1 over n plus. Now, this is going to be n times n minus 1, and the rest will get killed off by this. And on the bottom, you have n squared. So one of the n's in the bottom killed off that n on top. And then you have n minus 1 on the bottom. Okay. Let's clean this up a little bit more. And then you're going to be shocked at what we get. Just a complicated way of writing down the following number. Well, to make life easier, I will factor out the n minus 1. So I have 1 over n plus 1 over n times n minus 1. This is n minus 1 in front times, multiply top and bottom by n minus 1. So I have n minus 1 over n times n minus 1 plus 1 over n times n minus 1. So I have the n minus 1 in front times the denominators inside of this sum are the same. It's n times n minus 1. And so we add the numerators. If you have n and you take away 1, but you add the 1 back, you just get n. And amazingly, this answer is 1. Because the n minus 1's cancel out. And you're just left with n over n. And of course, n over n is 1. So the variance of x in this case is just the number 1. And this completes the section on covariance, variance of sums. I hope you enjoyed it.